Okay, good morning. Today is July 21st. We are going to go on with the study of, just a second, I have a question from Ms. Rubén. Estoy en clase, dígame, rapidito. Okay. Sorry. I would like to review the procedure to transform an arbitrary distribution of load into a series, sinusoidal series. Okay, that process. The two extremes are the uniformly distributed load, and the other is the concentrated forces. Okay. One thing that I would like to insist is that it's not just a procedure. Okay, it has to make some sense in your head, right? You see the distribution of loading, and according to that, you have to have the amplitudes of the series. Okay, so if this is symmetric, only symmetric terms has to be in the expansion, right? Opposite is the same, right? If you have a anti-symmetric function, of course you cannot express that with symmetric terms, right? So we're going to insist on that, okay? And then I would like you to start thinking about, see, this process looks like a little bit long, right? So let's think about what are the main steps that we have to take in order to complete this assignment, okay? I don't know if we will have time to start the next subchapter, which is about, okay, what we have done is consider or analyze a plate, rectangular plate, assuming that all edges are simply supported. But when you have a ship, right, you have the plate, and below that you have reinforcements, right? So the reinforcements prevents some rotation. Some certain way, it introduces some fixity, rigidity, right? So the rotation, okay, is somehow restricted. That means that on the edges, there's going to be some bending moment. So we're going to get close, but not exactly there, but close to the other end, which is the clamped situation. So we're going to emphasize what are the differences between simply supported and clamped, right? And let's see what we can, how far can we go, okay? That's more or less the agenda for today. Okay, so my full screen.
Yes, doctor.
Okay, so this is what we saw yesterday, or not yesterday, the other day. Okay, let's suppose we have a very strange distribution, okay? Load. Of course, it's virtually impossible to solve the application of this load directly into the differential equation of equilibrium of the plate. So what we do is we express this function into a, or not, expressed with a sinusoidal series. Since this is a 2D problem, we have two series, one in X and one in Y, they're combined. And somebody can think, oh, wait a minute, why do we use sinusoidal? Why do we use some other terms? The thing is that these terms will satisfy the boundary conditions. That's why we take advantage of that, okay? And since this is a linear problem, we can think that we can apply one term at a time, okay? And we have the solution of each one of these problems. That's something that we reviewed in the previous subchapter, right? So we have the solution for each one of these terms, okay? PMN, sine of m by x over a, and similar for the y direction. So we have that from the previous subchapter. So we could apply that solution to each one of these terms. And then we just simply combine. Why? Because the process is linear. The procedure that we are developing is linear. Okay, that's something which is very important. That's why when we developed the equation, the first thing that we did was let's recognize the characteristics. Okay, once you identify these characteristics, you can start thinking about, okay, what type of procedure can I apply to solve it? And I think the most important is that this problem is linear. Okay, so we could apply superposition. That means that you get one solution, another solution, and another solution. And the most general solution is a linear combination of those. Okay, that's because that's possible because we are facing a linear problem. Okay, now, in order to get this PMN, okay, this is the amplitude of each one of these terms. What we do is we multiply this equation by sine, okay, P and Q, and integrate over the whole domain, right? And we remember from our integral calculus that if you have this sine of m and sine of p in x, okay, if you integrate and m is different than p, the result is 0 because they are orthogonal, okay? The only choice that we have to get something different than 0 is that m be equal to p. Okay, so we got, if m is equal to p, then we will have to integrate sine squared mpi over x, mpx over a. Similarly for y, the only way where we can get something different than 0 is that n be equal to q. Okay, so in that case, we integrate sine squared in x, sine squared in y. And the result, maybe you remember, sine squared is equal to 1 minus 2 mpix over a divided by 2. So that's why we get a over 2 as a result. Those of you who do not recall this relation, please review your integral calculus notes. We need all of these, people. We need all of these. Okay, so be certain that you can solve it. I cannot do more than that. Okay. So, as a result of all of this, we obtain this expression. Okay, so we get here the integral of sine squared, we get an a over 2. The integral in y, we get a b over 2. And since this is what we want, we take 2 over a, 2 over b to the other side. And that's why we have some of this. Okay, for PMN. So this is the general expression that we can apply in order to obtain the amplitudes of each one of the terms of this expansion. So we can take any distribution load that we want to analyze and put it into here, and we can integrate. Okay. Now, if PXY would be very strange or very difficult to analyze, or you don't recall, okay, remember that you have always available to you the numerical integration, right? What's the rule that we usually apply, Mr. Soria, to numerically integrate something in naval engineering? Mr. Soria, do you remember the name of the integration rule? Mr. Soria, please. Do you remember the name of any integration rule?
Polar.
What? Come on.
Polar integration.
No, no. It's a changing variable, man. we're in trouble. Anyway, Mr. Chikaisa, do you remember any name, any method to integrate numerically?
Sorry, doctor, I don't remember right now.
People, if you don't remember
Simpson rule.
the name of numerical integration, man, we are in trouble.
Partial integration.
Simpson
No,
rule.
partial. Come on.
Simpson rule.
Yes. Yeah. Come on. Fortunately, this is being recorded. This is being recorded. So if you don't want to participate, yeah, that's fine, but it's being recorded. So, okay, let's continue. Now, this is one of the typical situations that we have to face, is the uniformly distributed load, right? For example, you want to analyze the plate at the bottom of the ship, right? It's basically the pressure is uniform, right? So that's typical situation, right? Even if you have some small variation, okay, as a first approximation, we could take an average value, okay? Of course, if you see that there is a large variation, you have to consider that, and we can integrate, but this is a classical situation. Now, in this case, as you can see here, the P is constant, of course, no, right? Because this is uniform. So this is constant. And please remember that P in this case has units of F over length squared, because this is force per area. Okay, so this has units of force per unit per length squared. So we put this into here, and since it is a constant, doesn't depend on sec of y, you can take that out of the integral. And now we can proceed and we can integrate. Okay, we can integrate. And here, this is something that we reviewed last session, is that when m is equal to even, right? In that case, this will get you 0. Okay, m is even, right? Because, for example, you get 2 pi x over a. If this is evaluated at a, you get cosine of 2 pi, which is equal to 1, minus cosine of 0, that's also 1. So the result is 0. Okay, the only values which are different than 0 are when m and n are odd. In that case, for example, for 1, you get cosine of pi, that's minus 1. Minus 1 minus cosine at 0, which is 1. So it's minus 1, that's minus 2. With this negative, that's what we here we get positive. People, these procedures are just integration. This is simple. We assume, we take it for granted. You are supposed to be able to develop those. Okay? And after doing that, this is what we obtain. Okay? Here we get a 2a and pi, and similar for the y. I forgot to include this p here. That's why I put it here. And this is the result. Okay, so we see that m and n need to be odd. If m or n are even, the result is going to give you 0. So m and n both have to be odd. Okay, and that's something that I want to emphasize this morning, right? Because if this is odd, okay, that's something that we draw here. Okay, for example, for 1, this is what we get for 1. You see that we have a line here, and you see that the distribution, okay, it's symmetric. So what happened here on the left is the same as happens on the right. And that's what we have this function here, okay? If we draw a line here, this part here is the same as this one here. So for m equal to 1, it's a symmetric function. So a symmetric function has to be employed to express a symmetric function, which is p equal constant. Okay, and that's why we cannot use any even function. Okay, See, let's suppose that we draw cosine of 2 pi x over a. So we have to complete one full cycle. This is sine of 2 pi x over a. And this is positive, and this is negative. So you integrate from here to here, the result is 0. And this is an anti-symmetric. And these are symmetric. And the function is symmetric. So you can use only symmetric sinusoidal terms to represent this function, which is symmetric. You cannot use any of this because it makes sense, right? If this is anti-symmetric, it makes no sense that you have to use dot in order to represent this, which is symmetric. Okay? Then we can proceed and we can express this function. Place this, this is the amplitude. This is the amplitude of just the load. Now, if you take any of these, okay, that's what we studied in 4.2. In 4.2 of this chapter, we studied the solution of the simply supported rectangular plate under a sinusoidal load. So you take this, and we know the solution. The solution is something like this. This is something that we already studied in the previous subchapter. Okay, we can write it here. This is from this is just a review. Okay, so what we're going to be doing, since this is a linear problem, is to apply each one of these terms one at a time. And we get this. And then what we can do is we can combine the solutions to each one of the particular terms, individual terms. Why? Because it's a linear problem. Okay, now, for this specifically case, for the uniformly distributed load, please, I see, we have gone through this topic many years. And that's something that we have to emphasize. Specifically, this result, this PMN, is specifically adequate for this type of loading. If you have a different type of loading, then you have to complete the integration, and you're going to obtain a different values for this term. Okay. So we replace this into here, and this is what we obtain. Okay, something which is very, very, very important is that you see that these expansions are from 1 to infinity. And nobody has the time to integrate until infinity, right? So one thing that we ask ourselves is, how far should I go? But that depends on the type of loading, okay? Something which is very important is, for example, for the load, I have m and n in the denominator. That means that as you increase m, the denominator is increasing, so the quotient is going to reduce. So we can expect that, for example, m equal to 100, this is going to be 1 over 100, probably 1 over 1,000. That's going to be very, very, very small. That means that we can stop the expansion at some point, because that's what we have to insist. For W, for the deflection part, which is something that we want to calculate, it's even better, because we have m and n to the square into the square. The square into the square. That means that if m or n is equal to, say, 10 or 11, okay, this is going to be 10 to the square into the fourth. So it's going to be very small. That means that to calculate this term here, probably you need 1 or 2 terms, and that's all what you need, because that decreases very rapidly. The people, this is specifically for the case of uniformly distributed load. Only for that case. Okay. I don't know if we checked units in this case. It would be nice if we use, what are the units of P? Mr. Ramirez, what are the units of P? Mr. Ramirez? Units of P? Mr. Ramirez?
Good morning, doctor.
Units of P? No? Mr. Dominguez, units of P, large P.
Length over force over length squared.
Force, exactly, force over length squared. Here, D is force times length. So you get P over D and you get 1 over length cubed. And you have A squared in the denominator, so that will give you length to the 4th in the numerator. So the result is going to be length. So potatoes and potatoes. Okay, this is an example that I completed. I just took this value. This is the value of the pressure on the bottom. You have it in your class notes. Okay. So this is the expansion first. Since we are expanding this function, this distribution of load, which is symmetric, we need only odd terms. Okay. So keep m with the value of 1, and I change the value of n. Then I change m, and I change the value of n, etc. So I go from 1 through 7, and we can apply the formula that we obtained for PMN. Let me remind it. 16. So this is 16 P over M and pi squared. So as you see, that we increase M or N, okay, we go downwards, you see that these numbers decreases. First one here is to the 4th, the last one here is to the 2nd. So there is a large difference between these and that. Okay, so now what we can do is we can go on and apply the combination. Okay, so what we can do now is we can say that P of xy is equal to what? Double summation for M and N. P Mn, which is these values which are in this table. And then we go sine n pi x over A, sine n pi y over B. So if you want to evaluate this at any point x, y, okay? So you pick a point x, y. So x and y are constant. And for those two, you can go and integrate and not integrate, evaluate for all of these terms. In this case, I go up to 7 only. Okay, and this is the result. So what I did was I changed x and y. Okay. This is this numbers here is the number of the partition. So I evaluated 50 values in this direction and 50 values in this direction for x and y. And for each one of these x and y values, I was evaluating this summation. And this is the result. Okay, and you see that this is supposed to be uniform. but we have some waviness, okay? You see that we have a large, then we decrease, a large, decrease, etc. If we include more and more terms, we will get closer to a uniform distribution. You see that the value that we should get is 20,000. And this 20,000 is about here. Okay, so this value is below, and this value is above 20,000. Okay, so we have some waviness because we need to include more terms than that. But we know that if we increase the number of terms, the terms which going to contribute not much. Okay, because this is small compared with this one. Okay, is there any problem with this procedure, people? Any problem with this procedure? Ms. Valdez, are you following me?
Yes, doctor.
Ms. Valdez, do you think you can do this plot in using Excel? Do you think you can do it?
I have to practice to look what it says.
Okay. Okay. See, what I do, I didn't do it with Excel because it takes too much, too many columns to evaluate each one of the terms. See, what I do is just do a little program, and that's it. We're going to talk about that in a minute, okay? That's why I want you to do this using a computer program, because this iteration, it's so easy to do it in a computer program. I mean, we just include a do loop and that's it. Okay, now, the only thing that we have done so far is to expand, to express this uniform distributed load with terms, with sinusoidal terms. That's all what we have done so far. Now, let's solve the plate bending problem. Okay, now, again, to do this is the expression that we have from chapter 4.2. Let me put it again. This is from, you don't remember, go back to 4.2, review it, and understand it. It's there. In 4.2, we solved the bending of the rectangular plate simply supported with a sinusoidal load applied on it. So we have this already. We just took the solution from there. So this is the amplitude of each one of the terms. Okay, again, here, it's very interesting that M and N decrease very rapidly. And you see here, okay, I have the two subindices, M and N, go down, increasing. So the denominator of this term will going to increase. If this is increased to the fourth power, of course, you can expect this to decrease very rapidly. And you see here, this is to the -7. This is to the -2. -2, -7. I'm going to raise your salary. I'm going to raise your salary. You throw a party, and the increment is going to be 10 to the -5 dollars. Put that in your mind. 10 to the -5. It's virtually nothing. Okay, so if you want to go on, yeah, you can do it, but you will going to be wasting time because the increments here, since you have both in the denominator, are going to be smaller. That's something that we always have to have in mind when we do these expansions. Okay, how far should we go in order to have close to the convergence? And that's something similar when you go to finite elements. Okay, you always have to be thinking about how close am I with the convergence. Now here, after calculating the amplitudes, okay, we do similar with the load. We have W, X, Y, is equal to double summation WMN. People, we are close to the third evaluation in 2 weeks, right? Try to help you. This is little w. This is big W, because this is the amplitude of that. Get confused. Something similar was the deflection and the shear force. Help so you avoid confusions. Here we go, sine m pi x over a sine m pi y over b. What you see here is that this is the W evaluated at the central point. And this is the deflection. Of course, this is a very special case, okay? This is X, this is Y, this is Z, and I measure W in this direction too. And the load is uniform. Okay, and this is simply supported over all edges. So it makes sense to have, let me change color. The deflection be something like this. So in the central point here, the maximum deflection. Okay. Since you can evaluate this, okay, on the borders, on the edges, and the sign will be 0. That's simply supported case. You can evaluate the slope. That's something we're going to discuss in a minute. We can evaluate the slope here. There's a slope in the X direction, it's going to be 0. There's a slope in the Y direction, it's going to be positive or negative. Anybody here? Mr. Gomez, the slope here, dW, dy, is going to be positive or negative here in this point here, where I'm signaling. dW, dy is going to be positive or negative?
Positive.
Yes, positive, because this is the direction of W. Mr. Ortega, here, in here, dW, dy is going to be positive or negative?
Good morning, doctor. Positive.
No, it's going to be negative. You differentiate the sign and you got a cosine. The cosine starts with one sign here and here changes sign. So you go here downwards and here you go upward. But in this case, since this is our reference system, you go upward, the slope is negative. But we have to be careful. We have to be careful. Now, the second derivative gives you the curvature. In this case that I'm drawing here, the curvature here, you see that it's open upward. So the curvature will have one sign only. Okay, so we can expect the bending moment to have one sign in general, because it's open in that direction. Okay, this is a simply supported case. You see, it's not just a matter of calculating something. There's a lot of information that we can deduce from here, from these results. That's what we call analysis. Okay. Okay, before we go on, here, okay, I'm sorry. Here, we have the summation of each one of these terms. Okay, we have this summation here, we have it here. And you see that if I take this value, right, this one here, and this one here, this, and that, you get very close to this. The other, this here, basically you have nothing. Up to the 5th decimal, this is 0. So you take this, 1, 1, 1, 3, and 3, 1. Those are the lowest. That's it. Probably that's enough for a good approximation. But remember, that depends on the type of loading. That's not always the case. Okay, so we take the load, we integrate it, obtain an expression for PMN, evaluated PMN up to a certain point where we feel comfortable. We take this PMN and apply it to calculate the WMN. That's the amplitude of the deflection terms. Okay, now let's go on. It's always recommended to you to evaluate 2 things. At least one is the deflection. That's something that we have done so far. And the other is the stress. In the case of the plate, how do you evaluate the stress? Ms. Arechua, how do you get the stress? What do you need for the stress? Ms. Arechua, in this case of the plate.
Yes,
Arechua,
doctor.
please. Yes, what do you need in order to calculate the stress, normal stress?
The moment.
Exactly, the bending moment. So for any casualty, do you remember the expression for mx?
The expression for mx.
Yeah, the bending moment.
Oh no.
I know it's difficult. Yeah, but Mr. Tenemea, do you remember the expression for mx?
Yes, doctor. For this case is the minus d by the wxx minus position plus position rate ratio and wyy.
Yeah. So you go integrate, evaluate load, evaluate deflection, evaluate moment, and as Ms. Arechua said, with the moment, finally you get stress. So let's go on to the next step. We have to evaluate the moment. Now, here, we have to insist that for the rectangular plate, in the case of the uniformly distributed load, the curvature in the y direction, that's the shortest direction, is larger than in the other direction. We can put it in somewhere over here, so you can remember. When A is larger than B, okay, and for this case, uniformly distributed load, WYY is larger than WXX. Because when you differentiate, you get M pi over B. B is smaller, okay, and this is because, okay, pi over B is larger than pi over A. When you differentiate with respect to X, you get A in the denominator. And when you differentiate with respect to Y, you get a B in the denominator. So in general, that's the case, okay? So this is something that we usually read in the literature, right? You read something like, in the direction of the shortest dimension of the plate. Okay, let me write it here. So, in the direction shortest side of the plate. Okay, so in this direction, we have the largest stresses. That depends usually on the type of loading, but in general, you look in that direction. Just a good practice is to evaluate both, okay, in X and Y. But from the very beginning, you know that much probably the largest stresses will be sigma Y in our reference system, Okay, it's always a good idea to evaluate both. But if you are short of time, go directly to sigma Y. Okay, now, here, with the formula that was recalled by Mr. Tenemea, we could apply this formula to evaluate my, I'm sorry. So this is the derivative, second derivative with respect to y, with respect to x. And what we said here, since b is smaller than a, this term here is larger than this one here. Now, again, WMN decreases with the sum index. But in this case, I have m and n in the numerator. So we can expect this combination to decrease because here I have m and n in the denominator to the fourth power. But they are multiplied by m and n to the second power. So in general, we expect to decrease, right? But not that fast as in the case of the deflection. Okay, and that's what we have here. Okay, in this case, okay, if you evaluate the sign on the edges, what are you going to obtain? So here I have a plate. This one here is going to be mx or my. Miss Santos. This one here is going to be mx or my. mx or my. It's easy to get confused, okay? So yeah, everybody should be practicing. Is this mx or my?
My.
My, yes, my. So okay, and Mr. Carranza, the value of this my in this point, what I'm signaling is how much? Is very high, very small? How much is it? Positive, negative? This value here
Is high.
Is it?
It is high. Yeah, I'm positive.
Okay.
0.
It's 0, yeah. Why is somebody said it's 0? Why is that 0?
Because it's simply supported.
Yeah, so remember that you have a support. Simple. It can rotate freely. There is no restriction to rotation. So the bending moment is 0. That's a boundary condition. Right? So we go to the maximum, and the maximum, of course, occur in the center. So these two functions are evaluated at a/2 and b/2. If we evaluate around the edges, the result is going to be 0. So that's not very interesting. Okay. Okay. Now here we have evaluated both, not only in y but also in x. Okay. See that the first term, it's to this value, and the last one here is about 1,000 smaller, or at least 500 times smaller than that. So that's, I mean, this is very small compared to this one. right? Now here I have 65, 14, here and 90. So this decreases, but not as fast as W. Okay, so we have to be careful with that. Okay, positive, positive, okay, because the curvature will be open upwards. Okay, so it's positive in both directions and everything is positive because the load forces to form a curvature like that. Okay. Top, you're going to have on the top surface, you're going to have positive or negative stresses on the top. Mr. Ramirez, no, I asked Mr. Pesantes, on the top of the surface, you're going to have positive or negative stresses here. Mr. Pesantes?
Is positive.
Do you agree with that, Mr. Romero? Positive or negative?
I think that is negative because it's compression surface.
Yeah, it's considered compression. You have something like that, forces like this, so on the top is going to be compression, on the bottom is going to be in tension. Okay, please, you have to be careful because when we go to finite elements, right, you have the plate bends. On one side, you're going to have one sign of the stress, on the other, you have a different sign, the opposite sign. And so you have to be careful with how you plot. What do you plot? You plot the stresses in the plate, yeah, but in what phase? Here, or in the middle of the thickness? Okay, so please be careful with that all the time. So, because you will see in finite elements that you have many results. And one of the first things that you have to do is ask yourself, does this make sense? And the sign of the stresses help you to answer that question. Okay, now the other type of loading that we're going to have here is the concentrated forces. Okay, so in this case we use a delta Dirac function, but this is a 2D problem. So this is a delta Dirac in X and Y. So the delta Dirac has units of 1 over length squared. If this is a force, the product will give you the correct units. The correct units, okay? So if we want to calculate PMN, well, we take this into here, okay? And we can proceed to integrate, okay? This is something that we did in chapter 3, okay? So if we have the product of a function f of x, okay, this is x, this is f of x, okay, this is f of x, multiplied by a delta Dirac, so this is delta x minus a. You multiply those two and integrate, okay, since delta is 0 except at a, okay, you can take that the product is going to be 0 except at that point. So you can say that f doesn't change much in the region where this delta Dirac is being applied. Since it doesn't change much, you can take that outside the integrand, and the result, it gives you that it's equal to f at a. That's something that we already reviewed. Okay, so if we apply that in our case, okay, so what we have to do is evaluate this function, okay, at the point where we apply, but we have to be careful because this point is specified with two values, x and y, okay? So we can say that PMN is equal to f sine evaluated at f, xf, yf, xf, yf is the point where you can see here where this force is being applied. Please be careful because the reference system, remember, points downward, it's positive. Downwards, positive. Downwards, positive for the external force. Okay? Okay, we can go on for a few seconds. This example I'm going to share with you. It's not in the class notes, but it's I don't think it's that complicated. What I did was I analyzed this plate, okay, using I think this is steel. You can recognize by the value of the Young modulus and the Poisson ratio. These are the dimensions of the plate. This is 4, this is 2 meters, this is 8 millimeters. So it's about this. So it's a good thickness, okay? It's a good thickness. Do you remember the thickness of the steel plate in the experiment? Anybody remembers the thickness in the experiment? Anybody? Who came to do the test? Mr. Benavides, did you do the test last week?
I did the aluminum test, but I checked it and was almost 1.8 millimeters, almost 2.
Yeah.
Yeah.
We have to check that. Miss Sayed, did you measure the thickness of the aluminum plate?
No, the aluminum, no. I checked the steel plate.
Okay. Okay, but it's a good idea for you people to start having things in reality, okay? The thickness was about that much, okay? So if for some reason you calculate something, for example, 1 centimeter, 1 centimeter is a good thickness for a plate. Okay, so when you calculate and obtain 1.5 centimeters, man, that's a plate like this. Okay, I'm gonna hit your head with this thickness. It's a very large thing. So try to start having these things in your head. Okay, for example, when I say 4 by 2, okay, try to do this. Okay, 4 is from there to there. By 2, this from there. So that's the plate that you are analyzing. So try to start thinking, try to start converting these mathematical problems into a physical problem. Try to start seeing, okay, how much this is going to be. Okay. Okay, now we have 2 applied forces, one here and one here, concentrated, not 1, but 2. But the process is the same. Why? Because this is a linear problem, and we can apply, we can superimpose solutions. So this is the general expression, PMN. This is a general expression. So in this case, we have to express this loading distribution like this. Okay, this is negative. Remember, this is going up, but downward is positive. Be careful with that. Similarly for the other one. At the end, we're going to take both with the same value. We can go on and integrate. Okay, we can take this, put it into here. And the result is going to be evaluation of this function at the points of the application. So this is the function. So you have to evaluate this at here and here. And this is the result that we have here. So we have x1, y1, that's this point, x2, y2, and this point here. And F, units of force, A and length squared. Force, length squared, force, length squared. Let's take a break. And when we continue, we can go on with this example, okay? So let's take 5-minute break here. Misayo, you can stop recording.